This video will serve as a review on graphing tangent and cotangent. For starters, we have tangent here, the parent function of tangent. We can see that the period, which is the distance between cycles, is going to be pi. The distance between periods is going to be pi. We can see for the range, it does go up forever and down forever. And then the domain, it's all real numbers except for where the asymptotes are, because we remember from our unit circle that tangent is undefined in quite a few places. Right, there are quite a few places tangent is undefined, and those are our asymptotes here. Tangent of pi over 2, tangent of 3 pi over 2, in distances of pi. The one thing we also want to remember, and I drew this circle in class, but I'll kind of draw it again. When we did the unit circle, we had the unit circle here. I'll try and center it. It'll let me. When we did the unit circle, we had different trig functions having different values in different quadrants. Okay, so for example, tangent and cotangent, we'll just do both, are positive in quadrant 1, and that's because sine and cosine are both positive. Tangent and cotangent are negative in quadrant 2, and that's because cosine is negative and sine is positive. Tangent and cotangent are positive in quadrant 3 because both sine and cosine are negative. And then tangent and cotangent are negative in quadrant 4 because while cosine is positive, sine is negative. And that is how we kind of figure out the direction of the curve, right? We know that this is 0 right here, and this is pi over 2. So from 0 to pi over 2, tangent is going to be positive. That means the output is positive. It's above the x-axis. So here we have 0 to pi over 2. And we can see that the function is above the x-axis. And then from pi over 2 to pi, which is this, all of the between, we can see that tangent is negative. So it is below the x-axis. And that kind of continues on as it cycles. Okay, here are the properties of tangent and the parent function, and then when it's been transformed, we can see that the period is pi divided by b. That's different than sine, cosine, secant, and cosecant. So very carefully thinking, because of the fact that it repeats every pi, the period is going to be pi divided by b. The phase line and the phase shift, my apologies, the phase shift and the midline intersection are going to be C over B. That's another way you can think of it. Or solve for x when you set bx minus c equal to 0. Now, what's important to note here is that my start point is normally 0, 0. So this is different for tangent and cotangent. My start point is normally 0, 0. Okay, and that's where we kind of start. My start point for a transformed tangent function is going to be my phase shift, comma, the vertical shift, whatever the midline is, because essentially it's wherever 0, 0 was shifted around. Midline is again always going to be that vertical shift, so y equals d. My increment is period divided by 2, and that's because with our starting point, I've got negative pi over 2 here. This will call 0, 0. And I've got pi over 2 here. Well, my kind of increments, this right here is my period from here to here. And so I just need to break it into these two pieces. And so both of these, if I want to break something into two pieces, it'll be my period divided by 2. Okay, before we get into the graphing, there's two things I want to show you that we didn't talk too much about in class. The first one is if it's negative, and I'm only going to show you it for tangent, but it's the same for cotangent. When I have a negative outside of the exponent, or outside of the function, that is going to be a vertical reflection, which means it's flipped over the horizontal axes. So let's see if this will load. I made this Desmos thing that you can view with a slider, so we can see tangent of x is in red there, and then negative tangent of x in blue is just the flip of it, right? So it almost looks exactly like cotangent, we'll see, but it's essentially going the opposite direction. So kind of when looking left to right, tangent goes down then up, negative tangent is up then down. Okay, and then you can see this formula I have is a slider to represent the asymptotes, because you have an asymptote starting at pi over 2 every pi, because that's the distance of one period. Other thing to talk about is, what does the A in front do? What does this A in front do of cotangent and tangent? And that is the amplitude. And it is a vertical stretch, so it affects the graph in the same way. Now, we are only doing sketches, so it's not going to really affect us, but it does affect the steepness. So you can see when A is 1, when A is 1, it's just our normal, it's our normal function. But then as A gets bigger and bigger, so there's our normal function, as A gets bigger, it gets kind of steeper and flatter. So we do want to make sure that when we're graphing it, if there is no amplitude, it has a good amount of curve to it. Okay, so let's actually graph one of these, see what we can do. So I got tangent of 2x minus pi plus 1. And so there's a couple things I need to find. I like to always just give myself a little sketch of the parent function so I can imagine it being moved around and such. So we've got our starting point at 0, 0 for the parent function. This probably needs to be moved over quite a bit. There we go. This will be x equals negative pi over 2, x equals pi over 2. And we're going to start down and then go up and over to the up, or up, over, and up. I don't know. But now I need to think about the transformation. So let's find my characteristics. We can start with period. Period is going to be pi divided by b, right? That's a little different because it's pi, not 2 pi. So b is 2, so that's going to be pi over 2. So now I need this distance. It's not going to be pi, it's going to be pi over 2. Then I can find my phase shift. Okay, I like to do c over b, super quick for me to identify, but you can also take 2x minus pi equal to 0, algebraically solve that, and you get x equals pi over 2. Okay, and then my midline is going to be y equals 1, and then my increment is going to be the period divided by 2. So we have pi over 2 divided by 2. We'll keep change flip, and we'll get pi over 4. Okay, so there is our there is all of the characteristics. Now at this point you can just graph it. You really just need to put your starting point and then go in both directions for your increment, alternating with a center point, an asymptote, a center point, an asymptote. Okay, sometimes I like to move this around a little bit just so I can kind of see what I should expect. It should be our phase shift, comma, 1, because that's my midline. And then my increment is pi over 4. So this distance right here and this distance right here should be pi over 4. So that's going to be 3 pi over 4 and 4 pi over 4, right? I'm just taking my center point, which is at pi over 2, and to get this one, I'm subtracting pi over 4, and to get this one, I'm adding pi over 4. Okay, let's sketch ourselves a graph. I think we're shooting for 5 periods. This doesn't matter as much, right? This doesn't have an amplitude, so it's not going to be very steep. And then here's how we do this. So my increment is pi over 4. So I'm going to put pi over 4 down. And then this would be 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6, 7, 8, 9, 10. This would be negative pi over 4, negative 2 pi over 4, negative 3 pi over 4, negative 4, negative 5, negative 6, negative 7, negative 8. I would say the easiest thing to do is to just keep the denominators the same, right? So I'll zoom in here for a second. 2 pi over 4 is the same as pi over 2, but I can just leave it as 2 pi over 4 so that I don't have to worry about simplifying or really struggle to count up, right? When you have the base the same, counting up is essentially, can I add 1? Okay, fill that in. And now I can go. So I'm going to place my starting point, right? Remember, tangent, it's the starting point that we move. So my starting point is going to be over pi over 2 and then up on my midline, okay? Sometimes I think it's helpful to just put the midline in there. And so it's going to be pi over 2, comma, midline, okay? Then I go 1 increment, and I've got myself an asymptote. And then I go another increment, and I should have a center point. I go another increment, and I have an asymptote, increment, point, increment, asymptote, increment, point, increment, asymptote. And we can go the other direction as well. So I would have an asymptote here, a point here, an asymptote here. So with sine and cosine, I definitely like to plot, sketch all 5 points and then plot them. But honestly, with tangent and cotangent, once you have either the starting point or the starting asymptote, you can really just kind of go for it. Because basically every other point is going to be an asymptote, or every other increment is going to be an asymptote or a point. Now, this was not reflected, so that means it starts down and goes up. So let's really clearly start down, follow the asymptote, curve over, and then curve this way. I need to follow along the asymptote, curve up and go over. I need to follow along the asymptote, up and over, follow along the asymptote, up and over. Again, we're just giving ourselves a best sketch. There should definitely be some curve to this one because it doesn't have an amplitude. Okay, so they're not all perfect. They don't all look exactly the same, but the idea is there, and that is how we graph tangent. All right, let's go ahead and graph a cotangent function now. Here's the parent function for cotangent. Still, when we look at our unit circle, we've got positive, negative, positive, negative. Even though it looks like it's going a different direction, it actually looks like that because remember, cotangent is going to be undefined here and here, whereas tangent was undefined here and here. So it's actually my asymptotes that have shifted, not where the function is positive and negative. So we can see that I'll have my asymptotes at 0, 2 pi, that's going to be right here, and then pi. That accounts for my asymptotes. My function is positive, it's above the x-axis, from 0 to pi over 2. And my function is negative from pi over 2 to pi. My function is again positive from pi to 3 pi over 2. And then again, we go back negative. So that is why it looks like it is curving the other way. I don't have Desmos graphics for negative cotangent and like when there's an amplitude, but the idea is the same, right? It would be vertically reflected. So this dotted line here is what negative cotangent of x would look like, which is very similar to tangent of x. Okay, the characteristics are all the same. I find the period by doing pi divided by b. I do the phase shift by doing bx minus c equal to 0, or that's essentially solving c over b. This gives us our first vertical asymptote. So instead of the starting point being 0, 0, the starting thing we want to find is this asymptote right here. So this is like, it's not a starting point, but it's our starting, maybe we'll call it our starting spot. It's our starting thing. that's the first thing we graph, and then we just count the increments in both directions. And again, we do the pattern where we go, center point, asymptote, center point, asymptote. There's other ways to graph it, but I do think just figuring out where your first vertical asymptote is the easiest way to do it. Our midline is again going to be y equals d, our vertical shift, and then our increment will be our period divided by 2. So let's go ahead and do an example. Now we can see this one has an amplitude of 2, which means it will be fairly stretched out, just a little bit stretched out. But as we don't really have a basis for the vertical amplitudes or vertical stretches, don't worry too much about that. Okay, we're not going to get that specific. So I'm going to give myself a little sketch-a-rooney of the parent function. So our starting asymptote is at x equals 0. Our center point is pi over 2 comma 0. And then our other asymptote is at x equals pi. And that's the kind of stuff that is going to be shifted around. So we can say our period is 2 pi over b. Now b is 1/2. The variable is never, ever, ever. The variable is never going to be in your value, right? So we need to keep in mind that x divided by 2 is the same as 1/2 times x. Maybe I'll move that up there so we can see that b is 1/2. Okay, so that makes my period 2 pi times 2 over 1. My period's going to be 4 pi. Okay, that's going to be my period of this function. Okay, then next I can find my phase shift, which is going to give me my first vertical asymptote. C is going to be negative pi over 4 over b, which is 1/2. And then that's going to be negative 2 pi over 4, which is negative pi over 2. Again, you could also solve by setting this piece equal to 0, and it would give you the same thing. Okay, it's just personal preference. My vertical shift is negative 3, so y equals negative 3 is going to be my midline. And my increment, which is arguably one of the most important things here, is going to be my period divided by 2, so it's going to be 2 pi. So essentially, here's what happens. My phase shift is negative pi over 2. I'm going to the left, so this is going to become x equals negative pi over 2. The other asymptote is going to be a distance of 4 pi away. My center point is going to be a distance of 2 pi away. So essentially, I'll take negative pi over 2. I'll add 2 pi, which is really 4 pi over 2. And that will give me negative 3 pi over 2. I mean positive 3 pi over 2. So this is going to be positive 3 pi over 2, but I also shifted it down. So my midline's negative 3. It's going to be at negative 3. And then this one is another 2 pi over, which is going to be 7 pi over 2. Okay, and that's kind of how you're going to continue to count to find the points. But all I needed to know was this was negative pi over 2, and that my increment was 2 pi, and then I'm able to place everything else. So let's go ahead and put this on a graph. All right, I'm going to put my midline in here, and then I'm going to put my increments along the x. So my increment is 2 pi, but I'm not actually going to count up by 2 pi because my first point is a negative pi over 2. And I like having my graph like labeled in even increments. You technically could go like negative pi over 2 and then jump over here to 3 pi over 2 and then, only label it with that. But I like to show, okay, this is then 0, this is pi over 2, this is pi, this is 2 pi, this would be 5 pi over 2, so there's a 3 pi in there missing. This would be 3 pi, this would be 7 pi over 2. Okay, so that is going to be a pretty big gap for just one, right? So this right here would be one period. We want to graph 5 periods, which means that, I've drawn my increments a little too far apart. So I'm going to go in and draw them a little closer together, but you get the idea. I like to count up by over 2 because that's like the smallest base I have. So we'll say this is negative pi over 2. This will be pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2.
7 pi over 2, 9 pi over 2, 11 pi over 2, 13 pi over 2, 15 pi over 2, and we'll go this way a little bit as well. Negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2, I wish I had a fast forward button. I actually probably do, I just don't know how to use it.
Okay, so here's where we have to be careful though when we're counting off in increments of this. My increment for my graph is still 2 pi. So that means that the distance between my points still needs to be 2 pi. So honestly, I'm not even sure how many will fit on here, but I'm not labeling it again. So we're going to go with what we can get. Okay. So this means my starting asymptote is at negative pi over 2. So let me drop that line in. I know they're not supposed to be solid lines, but my dotted lines are not the best, so maybe I can change it. Okay, excellent. Then we're going to duplicate it. My next increment would be 2 pi away, which is going to be a full rotation, and that's going to be to 3 pi over 2. So we can see that's not where an asymptote is going to go. That's actually where my point is going to go, but it should go on my midline because this distance is 1 increment. I just didn't count up by that because it didn't make sense with having to start at negative pi over 2. So then I go another 2 pi. You can see that that's 1, 2, 3, 4 jumps. So I'm not going to be adding fractions anymore. I'm done adding fractions. I want to count jumps. So I'm going to say 1, 2, 3, 4. There is my asymptote. And then my next point is going to be 4 jumps from there. 1, 2, 3, 4, because that's an increment of 2 pi. And then my next asymptote will be from here. 1, 2, 3, 4 jumps. And then we can go the other direction as well. So 1, 2, 3, 4 jumps. And again, that's because this distance is 2 pi is going to be a point. And then 1, 2, 3, 4. And then let's see if we can fit another one. 1, 2, 3, 4. That's going to have us here. 1, 2, 3, 4. Okay. We're going to have to go with 4 periods because, again, I'm not graphing this again. So there's my asymptotes. Now this is cotangent. So we need to remember that cotangent starts up and goes down looking left to right, right? So we start positive and then we go negative, whereas tangent, when you look left to right, starts negative and goes positive. And whenever you forget, if you ever forget, I like to look back to the parent function and think, okay, this is where if this is pi, this is where cotangent is, and tangent kind of looks like this, but they're both positive in this first quadrant, right? So in my first little section, they should both be positive. So I'm going to follow along. I'm not going to start that high up. It's going to be maybe a little thinner than you would think to make it, but it's also been like very clearly horizontally stretched. So that's going to make it look a little curvier as well. So that's why we don't pay too much mind to the amplitude, because it's like, what do you want me to do? Ta-da! Done, did it. Awesome. That is all I've got.